Okay, so just a couple reminders before we get started today. Today is UVM's Student Research Conference. It's running all day today between 9 o'clock and 4:30. So if you have a break between classes, do try and make your way over to the Davis Center, Maple Ballroom on the top floor. Lots of undergraduates and graduate students are presenting some of the research they've done throughout the academic year there. Anyone here presenting there today? No? All right, regardless, there's a lot of interesting work on offer, so if you can make it over there, go have a look. Okay, let's talk a little bit about the final project. I put up the schedule, so just as a reminder, we're here on Thursday, May 11th, bright and early, 7:30 in the morning. Like I said, I don't get to pick your exam time, so I apologize. I will bring donuts and coffee to get us through. We will have slightly less than 3 hours of awesome robot videos and caffeine and sugar. Hopefully that will make things worthwhile. I put together the schedule so you can go and have a look now. We have 43 presentations to get through, so everyone has exactly 3 minutes and 30 seconds. We will have 2 10-minute breaks during the period. The way we do this is you are going to create a YouTube video that is exactly 3 minutes and 30 seconds long. You will be submitting the URL that points to that YouTube video the evening before. The TA will stitch all those 43 YouTube videos into a playlist, and at 7:30 a.m. we will press play on the playlist, and we will not press pause until the playlist finishes at 10:10 a.m. There will be 2 blank 10-minute videos in that playlist. That's how we keep everything on schedule. Questions?
It looks like from 28 to 29 there's no break.
From 28 to 29, there is a break. You're absolutely right. Okay, I will fix that. But there is here.
Yeah.
Okay, my Google spreadsheet skills are not what they should be. I will fix that. Okay, yes?
So we're not actually like presenting or giving a talk or anything?
You are giving a talk, yes. So your 3 minute and 30 second YouTube video will play without audio. When your video starts, you will walk up to the front of the room and talk over the video like you've seen me do many times now. It is surprisingly difficult to give such a short presentation. The key is to practice as best you can. Practice, practice, practice. Right? Okay. If you talk over your video and your video ends, or you talk long and your video ends, the next student is coming up to replace you. So again, practice, practice, practice. Right? You heard it here first. It's nothing personal. Everyone is going to keep to the 3 minutes and 30 second time limit. We've got lots of interesting work to present in a relatively short period of time. Okay, again, next week I'll put up a Google document that talks about exactly what's expected for the final project, but just to give you a heads up for what's coming. Any other questions? Okay, thank you for the heads up about the schedule. Deliverable, the 4th and final deliverable for the undergraduates is due on Monday night at 11:59, and for the graduate students, you're submitting your 9th deliverable at the same time. Another item that came up about PyroSim this week is that ID numbers need to be assigned contiguously. So if you send an object to PyroSim and you give that object an ID of 0, and the next object that you send to PyroSim has an ID of 2, you're going to have problems. Someone came across that this week. Same goes for the IDs of objects, joints, sensors, and neurons.
It sends them. I did that, and it just sends it as ID 0, 1, 2.
Ah, okay, good
So
catch. So it ignores 2 and replaces it with 1?
Yes.
Okay, good to know. Regardless, just make sure everything is sent, IDs are sent in a contiguous manner, right? It's easy to lose track of that if you're commenting objects and joints in and out of your code. Any other PyroSim intricacies you've discovered this week?
Yeah, so I sent you an email. I
Yes.
confirmed that
Oh.
you cannot obtain ray sensor data that are from the same multiple ray sensor data from the same object.
Okay.
It will show up in the robot, but
Okay.
it only takes the last ray sensor that's substantiated.
Okay, that makes sense, because you sent me a video where you can see that there are multiple ray sensors that are drawn, that are emanating from the same object,
Yeah.
which makes sense because those rays are drawn in a different part of the code than where the sensor data is generated.
Yeah.
So, one ray sensor per object. Other questions? Yes?
Just Windows errors with the collision of creating new objects.
Okay. So you're on a Windows machine and
Yeah.
you're not able to use the two new features.
Yeah, I'm trying to just like stack objects with like stairs.
Okay.
I'm just getting like Windows errors.
Okay.
I don't know exactly where to begin.
Exactly. All right. Send me an email. Maybe we can follow up offline about this.
Okay.
Other questions? Okay. So let's go back to lecture material. We're working our way through this final section on the course and looking at expanding an evolutionary algorithm so that the genotype encodes aspects of the robot's body along with the robot's neural controller. We looked last week and Tuesday at Carl Sims's first approach to this. We then looked at the application of Lindenmayer systems, which were originally designed to simulate biological growth. And we attached an L system to turtle graphics. So we have an L system which is telling a turtle how to move through an empty physics engine and build a robot body and brain as it goes. We ended that last time and we started it on lecture 25, which is entitled Why Evolve Bodies. Right? We've seen lots of different robots in this course by now, and you might come to the conclusion, why don't I just build a humanoid robot or a four-legged robot or a six-legged robot, build it by hand, and then take an evolutionary algorithm or a machine learning algorithm and get it to optimize just the neural controller of the robot, right? Why go to all the effort we saw in lectures 23 and 24 to create a relatively complicated algorithm that does both? It turns out that there are lots of questions, lots of answers to the question, why evolve bodies? And the one that we're focusing on in lecture 25 is that it turns out that if we include development, which is the fact that the robot's body is going to change over its lifetime, actually makes things easier, if you do this in the right way, makes things easier for evolution. Okay, so that's what we're looking at today. We'll finish that and we'll start in on lecture 26, and I'll talk about lecture 26 when we get there. Okay, so lecture 25, why evolve morphology, or why evolve bodies? So in this case, we're looking at Evo-Devo Robo. So we've got our robot, or in our cartoon here, a human which is behaving at the here and now time step, right? From second to second, the robot or organism is perceiving its world, reacting. When it reacts or moves, the sensory data changes. It changes how it moves, and we have this fast time scale of sensor motor actions, right? We're going to introduce in this experiment the ontogenetic or developmental time scale, where as the robot is moving about in the physics engine, its body itself is changing. Remember that an embodied agent, when it acts, it changes the sensory input that it gets. So as I'm moving about the room, my visual field, my visual perception is changing. That function between action and sensory reaction depends on my body. So as I'm changing my body, I'm changing how my actions affect what I perceive. So we're actually going to connect these two timescales. As the organism or the robot is changing over its lifetime, it's changing how it sees as a function of how it moves, right? To make things even more complicated, right? We have the slowest time scale down here, the evolutionary time scale, or the phylogenetic time scale, which is sculpting the initial body and brain of the robot. Just to reinforce one concept I mentioned last time, which is genetics or DNA is not really a blueprint, right? You can't look inside a biological DNA and see the final organism because there is no final organism, right? There is just some biological system that changes over a particular time scale. So genetics, or the genome of an organism, or in our case a robot, is not a blueprint, it's a recipe. It dictates how proteins interact and cells interact over time to produce different results at different points in time. Right? Very important concept. Okay, so we ended last time with this slide, which I will have to maximize so we can see the videos. I introduced this term morphological scaffolding. So you'll remember that we saw this idea of scaffolding before. Scaffolding is the idea that we make the environment easier for the learner, like putting training wheels on a bicycle so that the learner can start to understand the rudiments of bicycling. Once they start to understand the task, we gradually remove the training wheels. Skip ahead one slide. You remember right at the beginning of the course, I showed you this robot here, which evolves to grasp this blue object. This is an example of scaffolding. It's also known as shaping, synonyms for the same thing. When the robot evolves the ability to grasp that blue object, we change its environment and move the blue object slightly further away. Here's another passive dynamic walker, and on the right here, a hybrid dynamic walker. That was another example of scaffolding or shaping that we saw throughout this course. We didn't talk about Ryle and Husband's work here. This was one of the first experiments with the physics engine where they were evolving the biped to walk. And you'll notice those small black arrows here. When the biped starts to fall over, they would apply compensating external forces in the physics engine to push the robot back upright. So this is almost literally training wheels on a biped. Over evolutionary time, which is the green arrow here, these forces gradually decay until there are no more training wheels on the robot and it's freely walking with a biped gait. Right? So this is all environmental, where the environment is somehow shaping or scaffolding the robot. Here, we found that the robot's own morphology can apply scaffolding. So I showed you some of these videos last time. We had our standard experiment, which was working before, and I have no idea why it's not working now. Why are we not able to play these videos in here? Okay, bear with me a moment. I'm going to have to go find these videos. No such luck. Let's try one more time. Okay. I have no idea why this worked on Tuesday and not today. Who knows? Aha. Okay, this is going to be a little less elegant than actually doing it in the slide, but here we go. Let's go through our standard experiment where we don't have morphological scaffolding. We have this upright four-legged robot. and we want to evolve phototaxis. There's the light source in the top left, and here's the initial population of random controllers.
Was that one generation?
That was one generation, exactly, just marching through each of the random controllers in that initial population. And I'm going to confuse myself here now because I have so many videos. There's still the random one. We don't need that anymore. And here was the final gate that we got. Again, not a very elegant quadrupedal gate, but it gets the robot to the target object. It took quite a bit of evolutionary effort, quite a few generations to get to this point. Why?
Because you had to learn every single intricacy involved in getting to the final product, I guess.
Can you say that again?
It involved learning every little intricacy to get to the final product, as opposed to the new one we're learning about neural shaping, where you can teach it each step as what's walking first, then what's walking in direction, then what's walking quickly in direction.
Close. So the morphological scaffolding that we're going to see in a moment is going to make things more incremental from the point of view of the robot. Here we're sort of throwing the robot in the deep end, right? But in what sense? Why are things harder for the robot that has to start evolving upright compared to the one that I showed you last time that's going to start with a different body plan that's lying flat?
Because the focus on multiple things.
Multiple things, right? So what are the multiple things that evolution has to solve here?
Like balance.
Balance and
moving towards the
moving towards the light, right? So it's got to displace the robot towards the light source while keeping the robot from falling over, right? The fact that evolution has to perform these two or solve these two challenges at the same time means that the fitness landscape is pretty rugged, right? So you remember our discussion about fitness landscapes. We have along the horizontal plane of this landscape, we have aspects of the genotype, so that every point in the space corresponds to one genome, or in our case, one controller for the robot. And the height of any point in this fitness landscape is the fitness of the robot using that genome, right? So even if the robot happens to be here, it's happening to take a few steps towards the target, towards the light source. If there's a slight change in the genome as a result of mutation, it's probably going to mess up the robot's gait that it's already evolved, and it's going to do much worse, right? So you remember that it's very difficult to evolve controllers on a rough fitness landscape, right? We have a robot that's partially walking, we mutate the genome. What is the chance that we're going to get it to take a couple more steps? Very unlikely, much more likely that we're going to break the gait that's already evolving. Right? Okay, so this is sort of the standard thing that we've tried to do, and as I was just showing you, we can add in things to the environment to try and make things easier, or we can introduce development, which is that the robot's body is going to change over its lifetime. So let me see if I can figure this one out. So in the morphological scaffolding case, we're going to start with a different body plan, which is that the legs are oriented horizontally rather than vertically. Again, you're watching generation 0 here, and we're just playing each of the random controllers in the population generation 0. Even in these random controllers, there are a few of them where you actually see the robot moving a fair distance away from the origin, right? It's already easier for evolution to find controllers that move the robot. There's one of them. Okay. A short time later, if I can find it, this single controller evolves, which gets the robot to the target object. It took fewer generations to find a gate for this robot than it did to find a gait for the upright robot. So we already have evidence that by changing the robot's body, we've made things easier on evolution. So we already have an answer to our original question, why evolve the body of robots? Because some bodies make it easier for evolution to evolve controllers for whatever you want it to do. So we're kind of already done answering this question, but let's move on and explore this idea of development. Let's go back to the cartoon, for example, cartoon for a moment. Let's assume that we actually have a body plan in mind. We've already built a physical upright robot, so we know what the final body plan should be. But it turns out that evolving controllers for a biped robot is extremely difficult. So we're going to try and start by evolving controllers for a much more stable robot. Once we evolve a controller for the more stable robot, we're going to change development a little bit so that now we have a slightly less stable robot. Continue evolution on the less stable robot. Once we re-achieve a good controller, we're going to make the robot less stable again and carry on. Right? So we actually have a target robot in mind, this upright-legged robot. We now have this robot that's lying flat and gets to the target. What do we do at that point? Okay, so we have this flat robot here that gets to the target object. Now we're going to change development a little bit. You can actually see the robot developing now, where it starts its lifetime in the flat body configuration, and by the end of its lifetime, it's become an upright robot. So over its lifetime, its legs are becoming increasingly vertical. Yes?
I get two questions.
Sure.
Are the legs turning black because of touch sensors?
Yes, that's just us visualizing the touch sensors.
Also, to make it stand up, are you just putting the object, the desired destination, to be at a higher Z value?
Good question, right? You're all physics engines experts by now. So we're simulating development here. We're simulating the two timescales in this one video, right? We have slow developmental change, where the legs become increasingly vertical, and we have the rapid movement of the legs as the motor neurons send commands to the motorized joints. How are we simulating development in the physics engine?
Could you be restricting the joint?
We are restricting the joint. Which joint? How many joints does this robot have? I hear 5. There's more than 5. More than 6. 9, right? So we've got 4 legs, and you'll notice that the legs are rotating forward and backward relative to the main body, and horizontal inwards towards vertical. I mentioned a few weeks back that you can simulate your shoulder joint, right, which is able to do this, by putting 2 hinge joints together. You can connect object 1 to a small sphere, which you cannot see in this simulation, which is inside the corner of the main body. So that cylinder is attached to the sphere, which allows this movement. And then that small sphere, the ball and socket of your shoulder, if you like, that small sphere is attached with the second joint to the main body. And that sphere to main body joint rotates through this plane, right? So what we're doing is we're controlling that inner joint, if you like, and we are manually sending a command that slowly rotates that joint from the horizontal to the vertical. That's not part of the neural network controller. We're manually sending we're slowly changing the desired angle of that joint over the lifetime of the robot. The second outer hinge joint, if you like, this one, is being controlled as usual by a single motor neuron. Make sense? So one joint that we, the investigators, have control over, and the second joint, evolution has control over, right? So that's 2 joints. 2 times 4 legs gives us 8. Where's the 9th joint? Jack, where's the 9th joint here?
In between those 2 pieces of the body.
Yeah, so we can see we have this actuated spine in the center of the robot as well. So 9 joints here. Okay, so what you're watching, actually, let's see if I can play these 2 videos together. So this was the best controller we found with the flat robot. After this controller was discovered, we paused evolution and we made this change to the robot body. And then we unpaused evolution and let it continue evolving controllers for this body, the one in which the robot gradually transitions from lying flat on the ground to standing upright. So this is all the videos I'm going to show you now, 5 videos in a row. These are all snapshots at different points in evolutionary time. This was generation 0 with the random controllers. After a few generations, we discovered a successful gate. We changed the robot's body. We kept evolving. We continued evolving until evolution rediscovered a new controller that gets this robot to move. So far, so good. Let's come back to the fitness function here for the fitness landscape here for a moment to build up an intuition for what's going on. When the robot is flat, and I'm going to draw this with a little cartoon here. Imagine you're looking at this robot from behind. When the robot is flat, what does the fitness landscape look like? Is it smooth or rugged? It's smooth, right? So whatever the fitness landscape looks like, it's probably something like this, right? So if we have a particular neural network controller out here, which moves the flat robot 2 or 3 strokes, if you like, forward, any change to that controller is only going to change the movement of the robot a little bit because it's already flat. There aren't any mutations to this controller that's going to cause the robot to fall over because this robot is lying flat. It cannot fall over. So a mutation is either going to make it move slightly less coordinated or slightly more coordinated, which means its fitness is either going to go up slightly or go down slightly. Right? So by forcing the robot to lie flat on the ground, we've sort of introduced a new kind of training wheels, and those training wheels smooth the fitness landscape. As I mentioned, we then ran this until we got a controller that got the flat robot to move quickly. What happens when we then paused evolution and changed the robot so now over its lifetime it goes from the flat configuration to standing upright? What happens to the fitness landscape?
Does it return to the rugged landscape that has a decent starting position so it doesn't get stuck at other local optima?
It's possible, right? So definitely the landscape is going to become more rugged, but not too rugged because the robot still spends the first, 3/4 of its life more or less stable. So we're not going back to this very rugged fitness landscape. Maybe it gets a little bit more rugged, something like this. So the original controller that worked for the flat robot, when the flat robot now moves from its flat configuration to its upright configuration over its lifetime, this point no longer works, but it probably works pretty well, right? Because those 2 robots are not that different. So this fitness drops a little bit to here. Evolution continues until we get a new controller that works for the new body. Kelly.
What if you're trying to evolve this robot all the way to a bipedal robot? Would it just take forever?
Absolutely, it would take forever. If any of you have tried biped robots by now, it is extremely difficult, right? This is the whole point of this experiment. We're trying to find a way to make things easier for ultimately a biped, or in our case, an upright quadrupedal robot.
What constitutes a minor change? Like, would removing the middle spine be a major change for it, or adding 2 more legs to the side, would that be a major change?
No one knows, right? So this was an experiment we conducted a few years ago. Which morphological changes will give us this process that we want of making things easier, of evolving towards an ultimately upright, unstable robot? Good
Is
question.
it something that your lab has actually done though, like evolved one of these or something similar to that with more degrees of freedom into a biped, or?
We haven't gone all the way to the biped yet. We've done the quadruped, which you're seeing now. We'll see the hexapod in about 5 minutes' time. We have not done a biped yet. Okay. I know it's a little late for you to change your final project. Should have mentioned this at the beginning, right? Too many things to do. Okay, so let's carry on, right? We now have a flat that develops into an upright robot. We've got a success again, so I think you can probably figure out where we're going here. Let's see if I can kind of arrange this a little bit. Here were the initial random controllers, successful controller for the flat robot, successful controller for the flat to upright robot, and we kept going. Here's stage 4. It's a little hard to see what's going on here. The robot almost starts flat and transitions to the upright form even faster. And it sort of runs out of gas here at some point, but this was good enough for our purposes. Pause evolution for the last time, and then carry on in the 5th and final stage here, where the robot starts in the upright form and, give it enough time, walks to the target object. Okay, so that took 4 different stages to get there. Let's get back to the slides now. Took us 4 separate stages to get there, right? Evolving controllers on the flat robot, evolving controllers on the flat to the upright robot. The little inset graphic here is showing the center of mass of the robot over its lifetime, right? So the center of mass is rising as the robot gradually stands upright. In the 3rd phase, we started the robot half upright, the legs at 45 degrees, and then it stood up the full rest of the way over its lifetime. And in the 4th and final stage, like the non-scaffolding case, every robot starts in the physics engine upright and maintains that upright pose throughout. Okay? So this is a more complex experiment than this one. There's also more phases, but it turns out that we could evolve the upright robot to get to the target object with less generations in this run than in this run. So in morphological scaffolding, we were starting with the smooth fitness landscape, and by gradually making the robot's body less stable, the fitness landscape gradually became more and more mountainous or more and more rough. So at the end, we had just as rough a fitness landscape as before, but by adding these training wheels, we made things easier on evolution. Make sense? Okay. Okay, I'm going to walk you through, we didn't do just that experiment, we did a large number of experiments. I just walked you through the control case A up here, and I'm going to introduce some terminology here. So in experiment A, there was no physiological change. The robot's body never changed. All it did was the motor neurons controlled the joints. There was no phylogenetic change to the body, no change over the lifetime, and no ontogenetic change over the lifetime. Ontogenetic is lifetime. Phylogenetic is evolutionary, ontogenetic is developmental. In the second experiment that I just showed you here, B through E, we have change to the robot's body over phylogenetic time, right? Like the monkeys evolving into humans. And then in phase C, D, actually only in phase C and D, the robot's body, this is a different experiment. I'll come back to the one I just showed you in a moment. In this case, we only had phylogenetic change. In each of the 4 phases here, the robot did not change its body over its lifetime. We evolved controllers on this robot until we evolved a controller that worked. Then we changed the robot to this, continued evolution. with the robot like this, then like this, and then finally like this. So we have phylogenetic change, but over the lifetime of the robot, its body never changes. So far, so good. That's experiment number 2. Experiment number 3 is the one that I just showed you with a number of videos. So now we have phylogenetic change. We started with a flat robot. Now we also have ontogenetic change. So here in this case, in phase 1, it's going from the flat to upright. In the second case here, we go from the flat to the upright faster. So this is actually different ontogenetic change than what I just showed you in the videos. More ontogenetic change, so now we go from the flat to the upright over the first third of the robot's lifetime, and then it maintains that upright pose for the for the last 2/3 of its lifetime, and again we end in the upright form. Right? So here, like in the 5 videos I just showed you, we're combining phylogenetic change to the robot's body with ontogenetic change to the robot's body. So 3 experiments so far. So far, so good? All right, let's make this even more interesting. Now we're going to introduce topological change. So you'll notice here I introduced the term parametric change. So by parametric change, I mean we're going to change the robot's body by changing a particular parameter, which is the angle of the joints, or the angle of the legs. How vertical are the legs? So for each of the robots up here, we have one number, one parameter, which dictates how vertical the legs are. In topological change, we're actually going to change the topology of the robot altogether. And so to understand these cartoons, I'm going to show you another robot. This is actually the hexapod, but you'll notice that in these experiments now, the hexapod starts with no legs, and we're going to add legs over phylogenetic and ontogenetic time. So I doubt I can play these either. No? Okay. Sorry, you'll have to bear with me here for a moment. No, it's not these. No luck with videos today. Ah, okay, go figure. Okay, here's an example of topological change now. You'll notice we now have our hexapod instead of our quadruped. It starts in a legless form, and over its lifetime, its topology is changing. Right? It started as a 3-object creature and ended as a 3 + 6 = 9 part creature. Okay, physics engine gurus. How did we pull this one off? As you figured out by now, in a physics engine, at least Pyrosim, you cannot change the length of a cylinder during a simulation. Right? You send a length of a cylinder and that's it. That cylinder has the same length throughout. Right? The position and orientation of objects can change in a physics engine, but not their shape.
Are they like hidden within the box, and then as it goes on, they get pushed out and bent down more?
That's exactly what happens. So the two cylinders are packed inside the body segment horizontally, and then they are gradually pushed out of the box and made more vertical over the lifetime of the robot. How are they pushed out of the box? So this uses an actuator which we haven't seen yet, which is the linear actuator. So it's something like a piston, which is pushing the object out and bending it downwards as we go. So we now have for every leg here, we now have 3 joints. One which is controlled by the motor neuron, as we normally do. The second one, we're controlling and making the leg gradually more vertical. And the third joint is a piston, which is gradually pushing the leg out of the body segment. Make sense? Okay. So now these little cartoons hopefully make sense here. So in the 4th experiment that we did, 1, 2, 3, 4, we start with a legless robot, and there is only phylogenetic change, but no ontogenetic change. So each of these 4 different robots here never changes its body over its lifetime. This legless robot here, the snake robot if you like, keeps its snake-like form throughout its lifetime. Once evolution evolves a controller that gets the snake robot to the target object, we then add on these short legs here and we continue evolution with this form, then continue evolution with this form, then continue evolution with this form. So far, so good? If you look at the rightmost panel in each of these experiments, they all end with exactly the same robot, an upright legged robot. We're assuming that's the physical robot that we actually have, and we want to try and transfer controllers to it, right? What we're trying to do here is look at different kinds of training wheels, and including no training wheels at all. Okay, 5th experiment, we're going to put everything together now: phylogenetic change, ontogenetic change, and topological change. So the video that I just showed you with the hexapod is phase N here. The robot starts in the legless form lying on the ground, and over its lifetime it grows, quote unquote, legs that become increasingly long and increasingly vertical, right? Which makes the robot gradually less stable over its lifetime. Once evolution evolves a controller that gets this robot to the target object, we change the body again. So now the body grows these legs, but these legs grow faster, and it reaches the upright legged form in less time, in the first 2/3 of its lifetime, and then maintains the upright legged form for the last third. Then we accelerate this change again, and then finally at the end we throw this ontogenetic change away altogether, and we finish, as always, with an upright-legged robot. So we actually have 4 different kinds of training wheels, and a 5th experiment with no training wheels. You've already seen that no training wheels does not work very well. So my question to you is, which of these 4 training wheels works best? And by best, I mean that it takes the least number of generations for evolution to get to here and find a good controller for this guy. For those of you that have read ahead in this paper, please don't answer. Any ideas?
I would believe F through I would be the best key.
Okay, we have F through I. Any other ideas?
I want to say maybe N.
N through Q.
Oh, is it? Okay, yeah. N through Q.
Remember, each row here corresponds to one experiment, and each column here corresponds to different phases in that evolutionary run. Any other takers? No?
We'll go J through M.
Okay, good. All right, thank you. Thank you. All right. Okay, so again, this was just to show you sort of how this works. So this again, N through P. I just showed you this video where the hexapod grows from the legless to the legged form. Let's do this one more time just for clarity. Legless through the legged form. The legs are growing increasingly long and increasingly vertical. And then at the end of this experiment, we are going to the, actually, let me see if I can, yeah, let's just play this one. Okay. By the end, we're again ending with the upright legged form, right? I've shown you videos for the quadruped and the hexapod, but that's not really what's important here. What's important is how the body is changing over evolutionary time and developmental time. Okay, I'm going to keep piling on details here. Let's take the first three experiments that we saw. I initially did 100 evolutionary runs of this case, 100 runs of this case, and 100 runs of this case, with the light source placed immediately in front of the robot. And for each of these three experiments, I recorded on average, among the 100 evolutionary runs, how many robots did we have to evaluate? So not number of generations here, but just actually number of controllers. It took slightly more than 5,000 controllers in this case to get the robot to the light source. And it took a little bit more with this case and a little bit more with this case. So at this point in the experiment, we were a little bit nervous because it looked like adding training wheels on was actually making things harder for evolution compared to no training wheels. So this was not quite what we had expected, but we carried on anyways. We then did a bunch of other experiments where now we again did 100 evolutionary runs of each of these three, where now the target object was placed front left of the robot. So now we did 100 runs, 100 runs, 100 runs, so a total of 300 runs, 600 runs, 900 runs, 1,200 runs, 1,500 evolutionary runs. We have a supercomputer here at UVM. We kept the supercomputer running for quite a few days to get all these results. In this set of 3 runs here, the target object was in front of the robot. Here, the target object was pi over 16 radians to the robot's front and left, 2 pi over 16 radians, 3 pi over 16 radians, and then in this 5th set of runs here, the object was 45 degrees to the robot's front left. What happened as we made this change to the robot's environment?
The more it had to turn, the harder it was for no training wheels to perform.
Exactly.
Or it took longer for it.
It took longer, right? So the light gray bars are increasing in length, which means that for these the sequence of 5 different experiments, 5 different environments, the task is becoming harder on the no training wheels robots. And it's somewhat becoming more difficult for the training wheeled robots, but not as much. Why do you think that might be the case? What is it about the fact that the object is front left that makes this harder for the upright robot?
Since the upright robot has to turn, it's more likely to fall over.
Exactly, right? Remember, this landscape is rugged because even if we find a robot that takes 2 or 3 steps, any mutation might cause the robot to fall over, especially if it's taking steps and trying to turn at the same time. It's much more likely to fall over, right? So now we've got a pretty complex experiment where we're changing the body and we're changing the environment and seeing how that's making things harder or easier for evolution. So far, so good? Okay. Remember that I just showed you that there were 5 experiments. I'm only showing you the 3 here. These 2 are the parametric change, right? Just the orientation of the robot. The right-hand panel corresponds to the same 5 environments. The light gray bars are exactly the same. This is the no training wheeled robot. And now in this right-hand panel, the gray and black bars correspond to the 2 experiments with topological change. What's happening now? The story is getting a little more complicated now.
It seems for the 2 topological changes, the relation seems pretty consistent beyond any amount of turning. Where
consistent for any amount of turning?
it seems relatively consistent for any amount of turning.
For the black bar, right?
For the black and dark gray bar. the relationship between them, where the black bar is better than the gray bar with ontogenetic evolution.
Yeah. Ontogenetic body change here.
Yes.
So the black bar stays relatively the same height throughout these 5 experiments. What does the fact that the black bar stays at about the same height mean? So for this evolutionary process, these tasks are not any more difficult, right? Getting a robot to walk forward or walk and turn towards the light source that's front left, equally easy. What about this case, the dark gray bar? What's happening in this case?
Yeah.
It almost looks exponential, right? Maybe it is if we kept going.
It's a
Right.
circle, so it would eventually cut back. So, yeah.
So thank you for betting on J through M, but unfortunately J through M is the worst possible thing you can do. It's even worse than no training wheels. If you want to continue the metaphor, this is like putting training wheels on the front of the wheel and the back of the back wheel, right? You could put training wheels on a bicycle in the wrong place and actually make things way harder, right? Why is this particular kind of phylogenetic change, the body is changing over evolutionary time, why did this make things even harder for evolution than trying to evolve a controller for the upright-legged robot? This we hadn't expected, but it made sense in retrospect after we'd done these experiments. Why?
I don't know why. I thought it would be better because I chose third, but also because I thought because it had none of these legs, long legs to start with, it would have adapted better to getting there, so it would have been able to kind of better.
So that was a great observation. This robot, the snake robot, takes no time at all. Evolution, because there's only 2 joints, right? There's only 1 joint rotating the forward and back body. It gets that 2-object robot to the target object in no time at all. So we seemed like we were doing well, but in the long run, by the time we get to M, it's doing terribly. Why?
Is it because each subsequent, like the difference between J through K is a much more drastic change than the difference between N through O?
Absolutely, right? The switch between J through K. Imagine evolution has found a controller that gets the J robot to the target object, and then suddenly that same controller is replayed in the K robot. Suddenly there are 4 legs there that it's never seen before, right? The K robot might as well be a completely different robot, right? In essence, it sort of has to start again. This is like putting training wheels on the front of the front wheel of a bike and the back of a back wheel of the bike. The learner somehow manages to push the bicycle forward. Now you take the training wheels off and you put them on the right of the front wheel and the left of the back wheel, right? You're completely changing the task of riding a bicycle, right? By adding the legs onto the K robot, we're completely changing the task for evolution, which is to orchestrate the movement of these objects to get the robot to the target object. The J landscape is indeed very smooth, right? And we get a controller up here that gets the robot to the target object. We put the 4 legs on. The K robot still has a smooth fitness landscape, but it's a completely different fitness landscape. So the point that was good before drops, right? And you're in completely the wrong part of the space of possible controllers for this robot. Evolution says, okay, fine, I'll start from scratch. It evolves a controller that gets this robot to the target light source, and then suddenly we foist L on it, on evolution. It still has legs, so maybe this transition is not as disruptive as this transition, but it's still pretty disruptive.
I don't know what the robot did, but it looks like it didn't have to deal with balance until halfway through its evolutionary process.
That's also true, right? Where maybe we're putting things off too long, right? Whatever it is, this was not the right thing to do. So in N here, evolution still has to control a legless robot,
but it's all, even right in generation 0, evolution is experiencing, so to speak, the case of the upright, fully lengthened vertical legs, right? It's already, evolution is already getting a taste of what it's eventually going to have to tackle, right? Right up front. This case right here, right? And we just expose it to more and more of that situation until it can master it before. But now this case never shows up here or even here, only at the end, right? So yes, we can create different bodies for our robots, but we can also do it in the wrong way that makes things even more difficult for evolution. Okay. So as I said, we performed 100 evolutionary runs, another 100, which is 300, 600, 900, 1200, 1500, 1500, 3000 experiments so far. This was all with the quadruped. We did an additional 3000 runs with the hexapod, just to make sure that this result was general beyond just the quadruped. So we kept the supercomputer busy for quite a while in this case. We computed it after the fact, and we used 100, this would have taken 130 years on a laptop. So good thing we had the supercomputer. Okay, so what's going on here? This pattern looks more or less like this pattern, but there's a slight difference between this panel and this panel. What is it? It's got more asterisks on it. What do the asterisks represent? Any statistics majors here?
Outliers.
Not outliers. These are actually representing p-values, or they're telling us that the difference between this bar and this bar, 3 asterisks means this difference is real. There's a difference between this bar and this bar, but there's no asterisk next to it, which means it might have been just by chance that there was a difference between these bars. We can trust the fact that the height of these 2 bars is actually different by the fact that there are these asterisks here. So back here for the hexapod, even in the simpler environment, it made sense to have training wheels, and it really made sense to have training wheels when we get out to the more difficult environment. What's happening in this case? So here we're using the hexapod, and we're investigating topological change. So these are the robots that go from the legless to the legged form. What's happening in this set of experiments? Yeah?
The ontogenetic change isn't constant anymore.
Ontogenetic change is not constant anymore, right? So it's still, for the hexapod, it is pretty hard to turn while walking, harder than for the quadruped, so things got a little more difficult.
Could that be extrapolated on in the quadruped?
Possibly.
That maybe they're not exactly the same and they might increase.
Could be, could be. We still see that this dark gray bar is much higher than the light gray bar, because we started with our legless robot, and suddenly evolution saw 6 legs that it had never seen before and had to figure out how to control them. By this point out here, we're saving more than twice as much time by pushing our robots through this morphological change, by simulating the evolution of development, right? It's really useful here. The most surprising thing about this experiment is when you compare these results to these results. And I'm going to go back and forth between these 2 slides for a while until we digest what's going on here. Here, remember that each group of bars, or color, the difference in the brightness of the bars represents different robot bodies. The heights of the bars represent how many controllers evolution had to try out before evolution found a controller that got the robot to the target object. So height, the taller the bar here, the harder it was on evolution, right? So here, lower bars are better. For each of these 6,000 runs, I took the best controller at the end, the controller that got the upright legged robot to the target object. I took the best controller out of those 6,000 runs, which gave me 6,000 evolved controllers. I then replayed each of those controllers in the upright legged robot, but now I applied random external forces to the robot as it was moving. So I was simulating wind to see whether it would knock the robot over. And I measured the drop in performance as a percentage. So if I have a controller that got the robot to move 3 meters towards the target object, and then I poked it randomly when I replayed it, and it only traveled 1.5 meters, traveled half as far as it did before, there was a 50% drop in performance of the robot in the windy environment compared to the initial windless environment that it was evolved in. Make sense? Each one of these bars, remember, represents 100 evolutionary runs. So each bar now is reporting the average drop in performance for those 100 controllers. So now, the lower the drop in performance, the better, right? We'd like to see the bar get to 0%, which would tell us we have robust behavior. The robot travels just as far in the windy environment as it does in the windless environment. We never got there. Usually there was some drop in performance. So we're really measuring now robustness. The lower the bar, the more robust those controllers were. What's the relationship between morphological change, or our training wheels, and robustness? Which tended to produce more robust controllers? The light gray bars, the dark gray bars, or the black bars? The black bars. What I'll ask you to do is focus on this black bar relative to its neighboring 2 bars, and this black bar and its neighboring 2 bars as I go back and forth between the 2 slides. So for both the quadruped and for the hexapod, the black bars produced more robust controllers, and we got those robust controllers with less evaluations. We needed to run evolution for less time, and it gave us more robust behavior. Can everybody see that now? When we saw this result, we were really surprised. We thought this can't possibly make sense. I went back and checked all the results. I reran some of these experiments. And it turns out that when we have this case, start in the legless form and grow to the upright legged form, and then gradually accelerate that change until we throw it away. The N through Q case, which corresponds to the black bars here on the right, we get more robust controllers with less evolutionary effort. This doesn't seem to make a lot of sense. Remember back to your phototaxis experiments, right? In order to get robust phototaxis, in order to get a robot that would go towards the light source, regardless of where you placed it, you needed to evaluate every controller 4 times, right? You needed 4 times as many evaluations to produce robust phototaxis compared to just walking towards the light source 1 time. How is it possible? Took us a while to answer this question. How is it possible that in this case we got more robust behavior with less evolutionary effort?
Maybe just how it's evolving. It's already evolving with change, so it's already having to deal with some form of change. So there's something about how it evolved.
That's exactly right. Remember that the robots in the black bar experiments are experiencing morphological change not only over their lifetime, but over physiological change. I mentioned at the beginning of lecture today that a robot, or in our case, us, organisms, they experience changes to the body while they're trying to do things, you're experiencing different sensory repercussions to the same action, right? The sensor motor experience that I had when I was walking when I was 7 or 8 is very different from the sensor motor experience I have now as I walk at 43, right? So my body has changed from 7 to 43. I'm still trying to do the same thing, walk in a straight line, but it's very different, right? So not only do I know how to walk, but I have experienced walking in different physiological forms, right? Same thing with the robots in the black bar experiments. That might help me walk when there's a change in my environment, right? My body hasn't changed, but now my mass distribution is different because I'm holding an object, right? Same thing here. So these robots experience internal change while they're evolving, and then we 3D print them and we put them out in the world and they experience different environmental change, wind in this case, and they're more robust, right? So development here, which is where we started this lecture, development is not just a nice biological phenomenon that we can build into our experiments to make them more biologically realistic. They actually help us from a real engineering point of view, right? As an engineer, we would like to create a tool, in this case a robot, that takes less time to manufacture that tool. We can evolve fewer generations to get the robot we want, and that tool is more robust. Once we put it out in the world, it's able to deal with a wider range of situations than the robots that did not experience morphological change. Make sense? Okay, so in order to actually, we did these 6,000 experiments with our simulated robot. So I'm going to skip over some of these other experiments in the interest of time. We wanted to validate this on a physical robot, so we use state-of-the-art robot hardware here. This is the Lego Mindstorms robot construction kit. Let's see here if I can play these for you. Let's see. Okay. So I'm going to just walk you through the building of this. I put 2 Lego motors in the center here. These 2 Lego motors are going to simulate the actuated spine of the robot, which I haven't turned on yet, but just so you can see them. Okay. So again, I haven't turned on the motors yet, but you can see that the spine is somewhat different from the simulated robot in that we've got 1 degree of freedom in the spine and then if I can find it, 2nd degree of freedom in the spine. So we actually have, if you can imagine this, we've got a shoulder joint sitting in the center of this robot. So what we're actually going to do in the Lego robot is these 2 motors are going to move quickly, and they're going to simulate the here and now time scale, the sensor motor time scale of the robot. Then we built a gear train on the front and the back of the robot, so that the physical robot can simulate the parametric morphological change. So the robot can slowly go from the flat form to the upright form. So the inner 2 joints at the spine are going to move fast, and the outer ones are controlled by a 3rd and 4th motor, which are going to move slowly. So far, so good. And then we can put all this together. And I don't have that video here. Oh, yes. No, wait. Is this it? Let's see. Bear with me here. I think this is it. No, we saw that one already. Ah, here we go. Okay. Okay, so a little hard to see here, but we start with the robot lying more or less flat. And then as it's actuating the spine in the middle, you can see the front and the back legs gradually becoming more vertical. So,
Perfect.
not the most efficient or high-powered robot, but it's basically doing what we tried in simulation. So we're able to integrate on one robot the slower developmental change and the fast here and now change. Once we got that figured out, then we can grab, so that's the robot with the training wheels, the legs that go from horizontal to vertical. Once we got walking in the physical robot, we could remove the training wheels. We could remove the training wheels now, and without the two gear trains, so you'll notice that I've taken the gear trains off the front and the back. Without the training wheels, we can get a robot that walks. Again, a lot of this process with the physical robot we did manually, but at least in theory we can simulate the developmental and the fast time scale. It'd be nice to try and automate this at some point, but we haven't quite got there yet. Okay, any questions about this experiment? Okay, we're basically out of time, so just before we break here, what we will do is next Tuesday we'll start in on lecture 26, and on Thursday we will conclude the course with a guest lecture by Nick Cheney on soft robotics. You have a quiz due tonight, and your final deliverable is due on Monday night. Thanks very much. Have a good weekend.